Hello, this is lecture 7.4 of the GPU teaching kit. We'll be presenting atomic operation performance. The objective of this lecture is to learn about the main performance considerations of atomic operations. We'll learn about the latency and throughput of atomic operations. We will then study the performance of atomic operations in three scenarios: atomic operations on global memory, atomic operations on shared L2 cache, and atomic operation on shared memory. This slide shows some important details of atomic operations on global memory or DRAM. An atomic operation on a DRAM location starts with a read. On the right-hand side of the slide, we show the access path for that memory read. It comes out of the streaming multiprocessor through the DRAM channel into the DRAM bank, and the value needs to be accessed and travel through the DRAM channel back into the streaming multiprocessor. This whole path involves a latency of a few hundred cycles. The atomic operation will end with a write to the same memory location, the same path with a latency of a few hundred cycles. During this whole period of time, no one else can access the location. Now that we understand the execution timing of an atomic operation on a DRAM location, we can turn our attention to the execution timing of multiple atomic operations on a DRAM location. Each atomic operation involves a full DRAM read latency, a little bit of execution to generate a new value, and then a full DRAM write latency. So we show the timing as atomic operation N that will involve that two memory latencies and a small execution latency in the green dot. After the nth operation completes, the nth plus 1th atomic operation can begin, and that involves a DRAM read latency, a little bit of an execution delay for generating the new value, and then a full DRAM write latency. As we saw in the previous slide, the rate at which we can execute atomic operations on the same DRAM location is limited by the inverse of 2 times the memory latency. The DRAM latency in modern processors are a few hundred cycles, typically about 500 clock cycles. This means that if many threads attempt to do atomic operations on the same location, the memory throughput is now 1/1000 of the peak bandwidth. The phenomenon of drastically reduced throughput because of latency is not unique in computing. We all have some similar experience in supermarket checkout. Some customers realize that they missed an item after they started to check out. So they will run to the aisle and get to the item while the rest of the line waits. The rate of the checkout in this case is drastically reduced because of the long latency for the customer to run to the aisle and back. So now imagine that if we have a supermarket where every customer will start the checkout before they even fetch any item. So they start checkout and they go and shop and collect all the items and come back and finish the checkout. In that kind of scenario, the rate of the checkout will be 1/, the entire shopping time of each customer. And this will be a terrible, terrible throughput for the checkout line. Because the throughput of atomic operations is limited by the latency of the operation, there is great incentive to reduce the latency of atomic operations. This is an important reason why the more recent GPU devices provide L2 cache that captures all the atomic operations to DRAM and perform them in the L2 cache. The L2 cache has a latency about 1/10 of the DRAM latency. So if we capture all these atomic operations in L2 cache, we improve the throughput by about 10 times. And the L2 cache needs to be shared among all the thread blocks in order for this capture to work. And this is a free improvement on global memory atomics in the sense that the GPU kernels are still executing global memory atomics. It's just that the hardware under the hood captures all these atomic operations and perform them with about 1/10 of the latency and about 10 times the throughput. So these are free improvement for the programmers. The programmers do not need to make any change to their code to benefit from this improvement. Another important hardware improvement is to support atomic operations on shared memory locations. The shared memories have very short access latency. It's about 1/10 of the L2 cache access latency and about 1/100th of the DRAM access latency. Therefore, we improve the throughput by about 10 times compared to L2 atomics, or improve the throughput by about 100 times compared to DRAM atomics. However, shared memory is private to each thread block. Therefore, we need to make algorithm changes in order for the kernel to be able to limit the scope of atomic operations to within the thread blocks. And this will motivate the algorithm change with a technique called privatization that we will be covering in the next lecture. This concludes lecture 7.4 of the GPU teaching kit. Thank you.